Okay, so uh, this chapter, as we know, dealing with forces this entire way. And when we think about a force, just think like, for instance, an applied force. And what that means is we think of Newton's second law, especially when it comes to an applied force. So what would happen is the video that we'd seen yesterday with that of the Egyptians, to move them really large blocks of sandstone, how did that make it from point A to point B? How did historians theorize that perhaps happened? Yeah, on sleds, which would not be very efficient, but would be better than trying to push it across the ground because of all of this friction that you would see between two surfaces. Now, the best example when it comes to that of friction is that of sandpaper. Okay, and for anyone who's ever done any type of woodworking, we know, well, not that you would know, but what's true about the grain of sandpaper? Does anybody know? The larger the number, is that really fine, like paper like this, or is it really coarse? The the bigger the number, the bigger the number, the smoother. The smaller the number, it's really coarse. That's like 50 grain, and then maybe 200 grain if you're doing cabinetry type of work. Okay, well then you'd perhaps use 200 grain because you wouldn't want to scratch that top surface. Okay, and to me, that's one of the things I always call painting over plywood a cardinal sin. How many golfers do we have in here? So we've talked about cardinal sins before in golf, right? The first one, it's a par four. I don't know, this is 5.5 feet away. And then you're on the green in two, so you're putting for this birdie. So if you only putt it 4 feet, it never had a chance to go in. That's cardinal sin number one. Cardinal sin number two is if you're that far away, then you hit it by, then you hit it by again, then you finally make it. Three putting, that's the second cardinal sin. And then the third one is putting one in the drink or out of bounds or something like that. But for anyone who's ever played golf before, it's very easy to do. All right, so as we proceed forward then, uh, the sandpaper they're talking about, you can use your hand, although some people use maybe a motorized sander. So as that is turning around the drum, it's going to smooth that surface by applying friction. And of course, friction is going to create lots of what? Okay? For anyone who's ever been outside, whereas during the football season, as we get closer towards the sun going down at maybe, what would you say, 7:35, quarter to 8, it starts to get dark out, and all of a sudden the temperature starts to plummet. I think you would all would agree with that. So what you might do is you might do one of these, exhale on your hand, or do one of these, create a little friction. You can actually create quite a bit. The harder you push, the more heat you would generate, which is actually quite a bit. And in a couple combinations, you can create so much heat, you can probably get a blister on your hand. Might not think that's possible. Again, the faster and harder that you push in, you're going to create more and more heat. And it will eventually get to be the point, do that, you put it on your forehead, and you think, that is hot. Or you have someone reach their hand out, you put it in between there. Has anyone got cold hands? No, probably not. But you do that and you put it on there. Yeah, that's actually pretty warm then. Okay. So when it comes to this type of static friction that we see here, okay, that means, for instance, this desk, which really is not that hard to move, but bad design makes it hard to move. Because when this was put together, put the wheels too far to the outside. So then when you got this framing going around, these wheels can't swivel around in 360 degrees. So what it does is then it hits this side here, and it's hard to steer. So I just put it up on a cart and wheel it out that way. So sometimes if you're doing building designs, you kind of learn the hard way. Try to make that mistake only once. But in this case, if this desk was sitting flat on the floor like yours is now, it's not moving until you apply enough force to actually get it to move then. So that's what the Egyptians did, overcome that static friction, put it on a sled, and then a little more efficient than pushing across the ground. Then, when it was the Temple of Marcellus as being put up, you saw oxen in that example. So to move those large blocks, what did they do with the oxen then? Yeah, they made kind of like an oval, not quite a complete circle. You change that static friction then to what we would see here, rolling friction. Okay, so static friction, there's no movement. This is the Egyptians right here, the sliding friction on the sled, and then this is some of the other individuals. I don't know what nationality that would be. Babylonians, perhaps, that perhaps created the first type of wheel to move things. You're changing that sliding friction then to rolling friction. So, as far as basketball, NBA basketball is concerned, think of Detroit. Who's that? Why would they get what's a piston? It's what? It's the Motor City, or Motown. So Detroit's known for many type of things, baseball, football, music. If you ever heard of Motown, that's from the Motor City. So as far as pistons are concerned, what is a piston? Do we know? Yeah, it's actually what supplies the power. Okay, so again, just like in any other type of friction, are we mocking your team, the Detroit Pistons? No? All choked up about Detroit? The Lions, the Tigers? No? Okay. Anyway, so as that piston is moving up and down inside the valve, of course, how many of you check your own oil? Lift it up, pull the dipstick out, or is that what the computer's for? Unless the check engine light comes on or something like that. Pull the dipstick out, maybe you have to add some. Maybe yes, maybe no. But what is it that it doesn't eliminate that friction, but really reduces it? Oil. Okay? Because the enemy of any type of objects coming in motion is going to be friction. I don't know if it talks about, no, it doesn't talk about fluid friction, but that's what essentially you would use, is motor oil. Okay? Okay. So in this case, if you were a paratrooper for the Army, call it that, if you really wanted to, from the plane to get down to the ground really fast, what could you do to your profile? We'll call it that. Would you be like this, or would you do this? You pull your arms in, and upon doing that, you would decrease the amount of air resistance. Okay? So that would determine how fast the object will accelerate, because if you have your arms spread out like this, then what that's going to do is that's going to slow you down. It'll slow your acceleration down then as well. For anyone who's ever flown in a plane, is that anybody here? Okay, so and I haven't flown I was out of college before I ever flew. So it's one of them things to where, oh my gosh, I've never flown in an airplane. Well, I mean, not everyone has that opportunity. But one of the things that happens, what's on the trailing edge of that wing as it's coming down, making its final approach? What can that wing do? It's done by hydraulics. It actually tips down like this. What's that going to create on that plane, do you think? Starts with the letter D. Not downforce. You might do this across the ground. You pull it, what's that called? Drag. That increases a lot of drag on them wings. It slows or starts to decelerate that plane. Okay? So, does everyone have this information that wants it? Okay. All right. So, here's an opportunity again to, and to me, whether it's driving a bus route, shooting a free throw, working on problems, like I was just talking to this group over here, some of you ladies and gentlemen that are on the bus route that I drove, you might have been sitting at home thinking, where's the bus? I don't know if that went through your minds at all. Yes? Oh my. Oh, yeah. Yep. Well, that happens. So, as far as, again, any one of those aspects, the way you get better at them is, well, whether it's practice or in this, well, we won't call this practice, in problem solving, driving bus, shooting a free throw, throwing a football, catching, any one of those. So, hopefully we can appreciate this, that the more practice we do, the better I think you're going to get at this. Think of the first couple days when you're doing some of this problem solving. How many of you thought this is really, really difficult? Okay? And some of you maybe did. So compare to what you had accomplished from then till now. So there's not a lot of information in that problem, but there is just enough breadcrumbs in there to lead you to what the answer could possibly be. Did anyone watch is anyone a fan of the Rocky franchise? Okay. I don't know if people would rather follow like the older ones or the newer ones, because I see in the movie theaters now it's what, Rambo Last Blood?
Yeah, that's,
You want to see that?
I am going to that. Yeah. The Rambo. Oh, pretty bad. The Rambo movies are good.
Yeah.
It's in the name.
Mm-hmm, mm-hmm. But you know, the funny aspect about that, okay, we'll try to put this into perspective. How many of you like, for instance, like Greek mythology movies and things like that? One that comes to mind was called, was it Clash or Wrath of the Titans? I can't remember. But there was both, okay. But the first one, I think that was that Clash or Wrath, the first one? Well, we'll say it's Clash of the Titans, okay. I think that, we'll just say that was 2012. That wasn't the original Clash of the Titans. There was another one that was originally made, I want to say, in the 70s, I want to say. So with computer animation and computer graphics, if you had your choice to pick from, you'd probably rather see the second one just because of you would be more familiar with that. But with that first one, that was probably uh, pretty advanced for its time. So now when you look at some of these Rambo movies, you're saying that they look really good. But did you see the first ones that came out in the 80s? Did you like those that came out in the 80s?
Yeah.
Okay, fair enough. Okay, that's more so like your parents' time growing up when you were that age. So, okay, okay, all right. So regardless, um, my point is things are always going to change as you get older. Your tastes are going to change. Your maturity level is going to change. Because some of you might be thinking, gosh, this person sitting around me is so immature. Maybe yes, maybe no. That's for you to decide. Okay, so for those of you, okay, that maybe don't have the best understanding, what's the best thing that you could be doing right now? Writing this down. Because if you don't understand it, you're not making an attempt. How can we help you if you're not going to help yourself? I think there's something to be said for that. Is that type of logic make sense to yourself? How can we help you if you don't help yourself? Does that sound right? Okay. So in this case, a lot of you had already alluded to this. You've read the problem. What's the next thing that you should do? Okay, so you can't get hung up in saying that the final velocity is this or the acceleration is going to be that. You're going to want to know it by its labels. So, what do we know in this problem? So how do we know which one of them is a force? Because forces are labeled in newtons. Okay, so if we have a force of 1870, and I kind of make this problem up, I think, out of my opinion of the Rocky franchise, the fourth one where he goes to Russia and fights the Russian. He's got all this computerized equipment, and you can see him where he takes, in the movie, takes his fist and pounds on a force plate, and it reads out like 2170 newtons or something like that, which I find pretty hard to believe. But not if during the course of the movie you see the trainers taking this inside his muscles, stabbing him with a needle with what? Steroids. That's right, but Rocky, he's all natural, right? Yeah. Anyway, so we're making this problem based off of that. So 1870 newtons. What else do we know in this problem? 3.40 kilograms. What else do we know? And that's something that you have to think about. It doesn't give you that, but how do you know what the initial velocity is? If it starts from rest, that means what? That means 0. Okay? And we know the time. Okay? 0.30 seconds. Now, as you're looking at these, once you've wrote down all the information you know, next thing is, what's the question really asking? Okay? So if we're going to solve for momentum, we know that the product or the momentum equals what? True. Question mark. That's true too. So we don't have that. So of these three variables, which one do we have? We've got this one. We're missing these two. But when we look at this information, is there something that we can use to get just one step closer to finding this final velocity? We can use the force. That's correct. F equals ma. So why, you're right, but why are you right? Because we need to find the acceleration next, okay? So as we look at this, force equals ma. So if we have the force and we have the mass, now we can solve for this guy. Okay, so do what the formula tells you to do, which is what? No, we're not going to cross multiply. Right. Take our force, which we have in our setup, then you don't have to keep looking up in this problem. So 1870 equals, so what's on the right hand side? 3.40, because it tells us what our mass is right here, times what? Times A. Okay? So now, how do we get A by itself? Okay? We're going to divide this side by what? What are we going to do to this side? Same thing. So if they have canceled, our acceleration is what? Okay? 550. What though? Meters per second squared. Okay? Which, doesn't necessarily mean this is a real world problem. We're just taking you where the numbers would lead you. Okay, so now that you have the acceleration, now what do you think? Look at your formula sheet. What's it going to tell you? We're getting closer to this. We need to define that final velocity. Okay, so a lot of you are saying taking your acceleration, which is right, 550 equals and 0.30. Why don't we put our initial velocity there? Well, it's already 0, so it doesn't matter. Now, when it comes to doing these problems, yeah, I would agree it's probably difficult, but that's why we work on these. Okay? So, to solve for this then, how are we going to get our final velocity by ourselves? You said you can do this. There's nothing wrong with that. Okay? So what's 1 times VF? So what does VF equal then? If we cross multiply these two numbers, what are we going to do with these? 155. 165? Okay. 165 point blank, 0.0. Okay, and then that's meters per second. Okay. Now that we have our final velocity that we needed to find, what are we going to do with these two numbers now? Multiply them gives you your what? Your momentum, and that's what we're looking for. Okay? All right. Yeah, that's a pretty. I find it very hard to believe that his punch is going to be moving 300 miles an hour. That's a little too fast, I think. But when we're trying to write these problems off the top of our head, sometimes they don't come out how you would have envisioned. Okay. So, left outside, are we on the bus? I'm sorry, I didn't see it right away. Left middle. Okay, up. See, I'm looking for expressions. A lot of you are doing this. I'm just looking right past that. Sorry. Middle. See, you can't hide that. Okay. You're not hitchhiking, are you? No? Okay. Middle. Right middle. Right outside. And right outside. Okay. Fair enough. So, again, if you are struggling with these, you can come in for some extra one-on-one help. That would assist you, because sometimes that extra one-on-one attention is maybe all it takes to make a difference for that. Then you don't have all these other distractions about sitting here in class. And a lot of you are doing cooperative learning. That's fine too. But once we get to the point where we have some of these problem quizzes, that's where some people start to stumble. Because if you're just doing somebody else's work, that's not going to help you. Okay? And there's no reason to believe that anybody's doing that, but human nature as it is, that can sometimes happen. Okay, so we've got this paper here for you, and what does it say? When is it due? The 27th, which is Friday. Okay, we're mean, but we're not that mean. We're giving you holy cow. Tuesday night, Wednesday night, Thursday night. What are we thinking? Honestly, I'm thinking that you're busy. This isn't your only class, and it shouldn't be taught that you will do science all day long. Okay, that's not the approach that we want to take, because there are. Now I know why I printed so many papers out. I didn't hit double side. It's all single sided. I thought this was a lot. That is a very good question, and one I don't have an answer for. Since some of us wouldn't do all the papers for everybody, which I don't blame you. Okay, yeah, we'll maybe do an example. Okay, as Mr. Hoth is making those copies, for those of you who do have one, okay, what I want you to do is go ahead and take a look at one of the numbers on there, and we can work on that together. Don't worry, some of your papers are coming. It'll be a little bit. Number 5. Okay, one of the things I want you to keep in mind, okay? We said, but anyway, when it comes to newtons, okay, that's also a different way of giving you a weight, okay? Because it's the mass times the acceleration due to gravity. You could say that your book weighs this many newtons instead of pounds, okay? So forces measured in newtons and weights are the same thing. This ain't our living room, right? Okay? So, you said number 8 then? Uh, that one's just, it's not that difficult. So it just looks like it is. Maybe pick another one. That one's really not that difficult either.
What's the most difficult one?
The bigger number that you give, probably the more difficult. 15. Okay. So number 15. Now, I realize some of the copies are on their way, but number 15, it says, what force does a sledgehammer strike a crowbar if it hits the bar with a momentum of 385.15 kilograms per meter per second? So this is very similar to our Ms. Carly and Ms. Jasmine. One's swinging the sledgehammer, the other one's holding the crowbar. Okay? That's very similar to that problem. Okay, so the worker flinches at 1.90 meters per second and makes contact 0.58 seconds later. The mass of the hammer is 180 kilograms. Okay, now, again, the first thing you should do after reading the problem is what? Okay, so what do we know in the problem? What is the momentum? Kilograms per meter over second. What else do we know? What else do we know? Now, we'll just put velocity for now because sometimes there can be more than one. But what's the label for, or what's the number for this though? Okay, now, one of the things I want you to think about, okay, it says it was moving at 1.9 meters per second and then makes contact 0.58 seconds later. So that speed must have been which one if it hasn't made contact yet? It must have been the initial velocity. That is correct. And do we know anything else in this? Okay, what's the question ultimately asking for the force? Okay, so your force formula says you need to know two variables, mass and acceleration. Okay, so this is not a free-falling problem. So 9.8 is not going to be a value that you're going to use. So with the information that we have, okay, can we solve for that acceleration right now? No, we need to find that final velocity first because, okay, so we need to find this acceleration because we only have this variable and this one. We have two unknowns here. So, do we have enough information to solve for one of these? Yes, we do. And what would that be? Okay, so if we take our momentum, which is 385.15, what's that equal to? 180 Then what's your variable then? Final velocity. Okay? Oops. So how do we get that final velocity by itself? You're going to divide each side by what? So what's 385 divided by 180? Meters per second. Okay? So can we solve for our acceleration now? Yes, we can. So we're going to do what the formula tells you to do, which is acceleration equals what goes on top of that fraction? Minus all over what? Okay, so what do we do with these two numbers? Subtract them. And, okay, so 0.24 divided by 0.58 gives you what? Meters per second what? Now you can solve for your force. Okay? Because we have our acceleration, we have our mass, now we can solve for this guy. All right. So that was a lot of information we went over really quick. Okay? So, is there any questions? Because we went over a lot of content now. And I think it's time for you to give yourself a little bit of a mental break and ask any questions individually if you want. Is there anything else you want to discuss as a group? Okay, we will catch up to you next time.